Hi, my name is Naya. I'm from Augusta University. I'm really excited to have you all here to come listen to what I'm working on. So in my elevator pitch, I said I'm looking at a few different ways to apply implicit computational complexity. In this talk, I'm going to talk specifically about one of those things. Before I start talking about that, I want you to kind of, for this talk, adopt this kind of idea that I'm really interested about correctness. And what does it mean for a program to be correct and how to actually check that something is working correctly? Okay, so just keep that as a thought. If you look at my title, you should get the hint that I'm really interested in resource bounds. And I want to convince you that resource bounds are exciting. So just a few examples. In security, there's the idea of constant time programs. That doesn't mean it runs in constant time, but that you don't branch on secrets. I mention that because I think it's an interesting example where they embed this idea of time in the definition of to be correct, you have to have this time property. Another more practical example is that I can write a program and it can be syntactically correct, but it can still fail if it takes too long or it needs too much memory, and this is going to go wrong at runtime. So I actually have an example. I don't know if you've heard of Advent of Code. I really like Advent of Code. You get 2 programming problems every day. It's going on right now in the month of December. So I was doing it last year, and one of the problems they gave me is that you have this kind of 3-dimensional cube. And inside the cube, you have these 1-unit cubes, so the many cubes inside a bigger cube. So then they say, oh, just count how many of those unit cubes are on, and that is a very easy sort of binary, it's either on or off. So and then they said your cube size is 100 by 100 by 100. So I said, oh, this is very easy. Let me do a triply nested loop, and I just count. And so I solve my problem 1, I go on to the next problem, and they say, oh, the rules are the same, but now your cube dimensions are 400,000 in each direction. So it didn't work anymore. So this is a really real reminder of that came back to me and say, okay, I really need to think about how to do time and space efficiently, because I couldn't even solve that problem in my naive approach. I had to be more clever. So this brings me to my my topic. I have this idea that if we take implicit computational complexity, which is ICC, then applying that, we can get some new automatic ways to analyze program complexity properties, and it can also resolve some of the limitations that exist in the current ways of analyzing things. And not to leave you hanging, implicit computational complexity is a pretty big word. I want to explain what that means is you may have typically been used to thinking about it in terms of machine model and this kind of traditional way. So know that this is a complementary way to look at complexity. And the idea is that we're not concerned with the actual model that we're running on. It's more like you put in a language, a restriction, and then as long as you maintain this restriction, then you're guaranteed some complexity class. This is a definition I found from a habilitation thesis. It's very nice, so I like it. I included it here. It very much captures this idea of what it means to do implicit computational complexity. And the idea then is, if I'm a programmer and I'm using one of these implicit systems, it means that I need to figure out a way to write my program in the syntax that's provided to me, but in return, what I get is the guarantee that my program is in some class. And there are many different systems that fall under this umbrella of ICC, and many different ways that you could apply this. But I'm gonna show you as an example one very specific one that I like and I've studied a lot. So to give you a concrete example of what ICC looks like. This is a technique from this paper by Neil Jones and Lars Christensen. It's called the MWP flow analysis. The central question I'm asking here is that if I have a simple imperative program, and let's say this program has some inputs, so like the function inputs, What I want to know is after the computation is done, is the growth of that variable value polynomially bounded? Okay, so this is the idea we're looking at. And then in this paper, they present this way of MWP analysis that's going to answer this question. So I'm going to explain to you how it works. In MWP, you want to say that for your input variables, you want to track how much they depend on each other. And there are flows. They're called flows. So there's different characters that characterize this level of dependency. And there are different kinds of flows. So you can have 0, which means that there's no dependency between two variables. You can have M, which is a maximal linear. Then you have W, which is a weak polynomial. You can have P, which is a polynomial, and these increase in strength. So M is the weakest, P is the strongest, and that's how we get to MWP. It's from the names of these flows. And then there's a set of inference rules. By applying, we look at the program, we look at the semantics of the program and say, here's a statement. Then I have a rule how to analyze that statement. And from that, I get a vector. And I put those vectors in a matrix. And then I get a very nice matrix at the end of this analysis. Okay. So I'm going to show you an actual example. So here's my simple imperative program. It's using the syntax of this analysis. And on the right there, that's a matrix. It's an identity matrix. We put M on the diagonal and 0 everywhere else. So this is kind of the starting point. So here's how my analysis proceeds. So kind of like a parser, I'm going to go into this statement here, and I'm going to say, what does that do? And I have an inference rule here that tells me that if I see this exact statement, I need to update my matrix and put a P in that spot that I have indicated there. I've left out the inference rule to simplify this, but this is how it will apply. So the next step is I have an else statement. I have to go into this branch. So I have to look at what happens in the false branch, and it's very similar. So if in the last case I got a P there, now I'm going to get a P for that one. And again, it's the same rule that I'm applying, but I update my matrix. Then I look at this whole statement, and then what it actually does is say, do the addition of these two matrices, so I get to that result. And that completes my analysis of this first statement of the if-else command. So next step, I have to look at this while block. One thing that I need to say here is that every time I'm analyzing something, I'm resetting my matrix to the identity. So I'm going here back and I'm saying that I have the identity matrix, and then if I apply the rule here, I get 2 W's. That's again an inference rule. And then from there, I have to look at the while loop. That's the parent statement there. In that while loop analysis, I'm going to do a fixed point of the matrix. So apply the matrix by itself until it's no longer changing. For this example, it was super easy because it doesn't change when I do the fixed point. So that completes the analysis for that block. There's one more step. So when I have multiple commands, I have to put these together. So what that means is for the if matrix that I got earlier, and for the while matrix that I got in the previous step, I'm going to compute the matrix product of those two. And that gives me the final answer, which is, it looks like this. So for this program, that one on the right is its MWP matrix. Okay. There's a lot of things I could say here. So in the inference rules, there's some non-determinism. So there could be other matrices that can be used to type this program. This is one example. It could also be the case that the analysis fails if I have a state in my matrix where I cannot apply any rules. So it can also fail. But ideally, if you can complete the analysis, then I know for these input variables, my x1, x2, x3, then I know their growth is polynomially bounded. Okay. The result of the analysis is the idea that if we can actually complete the derivation, then we know that the input bound is, or the input value growth is polynomially bounded. In the paper, they give this very nice soundness theorem here and says if I have this syntactic property, then the semantic property follows from it. So that if my program is derivable, then I have polynomial bounded growth. That's the idea. But then I'm going to ask you, I said in the beginning, and I really want to be concerned with correctness here. How do I know that this is true? Okay, and that's really where I get to my work here. So I want to make sure that this actually is a true statement. Okay. So if my goal is to say that some property holds with the strongest possible guarantee, what I'm going to do is I want to use an interactive theorem prover. There are many different kinds of theorem provers, but I will choose one. I'll tell you later. The idea is that with the mechanical proof approach, I can make very strong logical statements, and then I can afterwards check it with the machine that this is actually correct. So this is a stronger guarantee of correctness than I would get with the paper proof, for instance. There is a cost to it. So if you write a proof, you're going to have to specify every single step of this proof that you're doing, and this is very time consuming. But then in return, you get the strongest possible guarantee. So you really have to think of, what I'm trying to do here, is it worth the effort? And to me, this is worth the effort, so I'm going to try to do it. My actual goal is to try to prove the MWP analysis. That's the one that I presented. I want to prove it exactly how it's outlined in the paper. And I'm going to use Coq Proof Assistant to do it. I have different reasons why I think it's a good, I've seen it used in different kind of applications where it's been successful. So that's kind of my intuition why I think it would be a good fit here. I'm specifically using the original paper because the original paper has the proofs. And that gives me a very good guide of how to follow to actually complete this task. But I put it in the open box there because I am not done. It's my to-do list. I have sort of broken this task down into steps of what I feel that I need to do and how this is going to look. And I think this is a big part of my dissertation thesis to complete these. So I'll tell you what I'm doing. It's a 4-step plan, okay? First, I'm going to need to define the language. That's a simple imperative language that I'm analyzing. It has certain arithmetic Boolean expression commands, and I need to define those in Coq. I have completed this step pretty much, so I essentially understand what I'm doing there. It's really important to get it correctly because if I don't get that part correctly, the rest of it is not going to go through very nicely. Once I've done that, I need to look at the mathematics of it. So I need to define my matrices. There's a semi-ring, and then the analysis introduces certain mathematical things that are kind of unique to it. So there's a thing called honest polynomial, which is used to represent the bounds. So I need to figure out a way to how to represent all of these in Coq so I can make progress in my proof. Then I need to define my inference rules and the actual analysis. This is going to put together the language and the mathematics, and then everything's going to come together very nicely. I mentioned that there was some non-determinism here. I'm not this far, so I'll have to see how that goes, but that's a pretty big deal with this analysis. But that's sort of the foundational work of what I need to do. And from that, I can then prove my lemmas and my theorems. The soundness proof, that's the main result of the original paper, so that's super important that I can prove that one. That's to say that the syntactic property implies the semantic. And this is a motivational quote here I have included, that these proofs are long, technical, and occasionally highly non-trivial. So I hope I can do it. I mean, But I mean, I think it's a really good thing that I have the proofs in the first place. So I'm taking a lot of encouragement from that. So that is my goal. If I can finish all my steps, then I'm going to be able to say that, hey, here's a formally verified complexity analysis technique. And based on my literature review, nobody has quite achieved that yet. They would show that when you actually complete your derivation on the program and you get that matrix, then that actually means that you have a polynomial growth bound on the input values. So this is a way to guarantee the correctness of it. And that's my goal. I made a little timeline just to indicate how far I am. It's a visual. Those are my 4 steps. And actually what is not apparent in what I'm doing is I'm having to do a lot of learning. And these are kind of the things I got to learn to be able to do those steps. So it's a sort of very two-way thing of learn this so that you can do this, and then learn this and do that. So that's what it's looking like for me right now. But let's just be optimistic and say I can finish my proof task and I have formally verified my analysis technique. So there's a lot of things you can do with that from there. If I certify the technique itself, then what you can do is you can make a formally verified static analyzer for complexity using this technique. But there's a gotcha. So my collaborators and I, we've actually worked on this MWP analysis before. And what we know from before is because of the non-determinism in it, it's not efficient. If you try to apply it, you can't just apply it. You have to modify the mathematical framework that it uses. But if you make those adjustments, then you can get actual practical analysis. So then there's a question of, could I take this adjusted system and prove that? Which it would be kind of similar, so I'm hopeful that this could be done. And then in that way, you could get certified static analyzer. So we'll see. This is my last slide. I'm opening it to questions. Yes.
Sounds like a really exciting project.
Yes.
So I'm just curious. So in the original paper, are there any static analyzers that are built using these methods already, just implementation-wise, without propagation, or?
Okay. I'll just repeat it. So the question was, is there a static analyzer built on the original method? And the answer is yes. We built it. It's for analyzing C programs, but it's a subset of C because the syntax is very simple. I actually have it here. So this is the syntax of the language. So as long as we're looking at C that includes these operations, then we can analyze it.
What's the analyzer implemented in? What language?
It's in Python. It's called PyMWP. Yes.
Thanks.
Yes.
So I may have missed a piece here, but I was curious about the MWP. It seems to only talk about polynomial bounds. What about beyond polynomial, exponential, and etc.? Is that possible? Is it excluded somehow by the input language?
So the question is, can we get other bounds? So I have a few thoughts about that. There's inside the mathematical structure, we define a semi-ring, and it's because of that semi-ring that we get a polynomial bound. My collaborators are very convinced that if we tweak that semi-ring a little bit, we could get maybe logarithmic bounds or different kind of complexity class.
Okay, but like some programs compute exponential results, right? I can multiply.
Okay.
And get an exponential value. So if the analysis can only conclude that something is directly dependent, polynomial dependent, and it's actually exponential. Okay.
So let me answer how that would.
I'm going to be correct.
Okay. So if your program is actually exponential or this, what's going to happen when you analyze it this way? You're going to fail to find a matrix to type that program. So you will not get a result. And this is another thing that the original paper doesn't really discuss. It says that you can try all these different non-deterministic ways to find your programming matrix, and if you can't find it, then you can have this guarantee of a bound, but it may fail. And this is a big problem when you actually try to put it in practical use, because you actually then have to think about what happens when analysis fails. So actually, the way to read this result is that when you don't get a bound, you don't know where it is. It's a sound method which says that if you get the matrix, then you're guaranteed polynomial. But if you're not getting an answer, then you don't know where it is.
Got it. Thank you.
Yeah. Yes.
Sorry. So since it's sound but not necessarily complete,
That's correct.
Is it tested on a suite of examples, or do we have like some idea of like how when it would, or what subclass it would generate matrices for sure, or?
We would have to look at that if we wanted to kind of characterize that answer.
Okay.
So you're currently in the stage of modeling the language, right?
I pretty much completed that, so I'm
right.
trying to do matrices.
Okay. So you said it's important that you get that first step correct. So if you're already done, how did you convince yourself that you actually like got this done correctly?
Oh, you can write a proof to say, well, it's about, you need to define that here's my arithmetic boolean is my commands. Then you can do a functional definition of how the operational semantics work. The relational semantics, you can prove that it's correct. I'm very much following, so I don't know if you're familiar with Software Foundation. They have an example of how to define the imp language, which is very, very similar to what I have here. The only difference is this little condition. So I had to add that, but otherwise that I'm following those steps, and I'm fairly convinced is correct, and I'm hoping that it is, that because I proved those things about the evaluation. And we'll see. Yes. Go ahead.
All right, so I'm trying to put on my doctoral symposium mentor hat, and it seems like the major challenge that is likely to occur in your work is since your main goal is to translate, for clarity, proofs from paper to talk.
Mm-hmm.
That's also where the potential difficulties are, right? That people write all sorts of things on paper, which if it's a reviewed paper, then they were perfectly convincing to the reviewers. But Coq has its particular algorithms for verifying things, and those are very different from the algorithms that are in the mind of a reviewer. So now I don't have a lot of personal experience with sort of translating paper to Coq, but have you thought about kind of what those challenges will be? Have you looked at the proofs as they are on paper and sort of analyzed, where is there kind of high-level human reasoning that might turn out to be more challenging in an automated proof assistant? So I don't know. I'm just kind of I don't have particular suggestions, but I'm suggesting a way to think about what the challenges might be, and kind of view of anticipating those, or maybe looking for related work where other people have kind of faced those same challenges, and you might look for inspiration to addressing them yourself.
Yes. Generally, a couple of things that I know about Coq that are going to be problematic is if you have any kind of classical assumptions of excluded middle.
Yeah.
This is not a thing. Maybe work around it. The other thing is that all your functions need to be decreasing, which I also believe that you can work around. Especially like, for instance, to do this while loop, you have to kind of give it gas and say that you will eventually terminate, because while loop doesn't necessarily terminate. So there are some tricks to getting around those technical issues. As far as the paper itself, I have gone over every single lemma and every single proof, and as far as what they say, to identify that these are the sort of high-level concepts that I need and what I need to define. I have not got too deep into the proofs themselves, other than it's long sometimes, but so the big question is that do I actually know this thing is going to work? Because if it's not correct in the way they define it, this whole work kind of falls flat. I have worked with it before, and I feel like if there was some major flaw in it, I would have noticed it. So that's sort of my confidence of maybe it's a leap of faith. We'll know when I finish. Go ahead.
Maybe tiny comment. If you find a major flaw, you can brag about it until the end of your PhD. It's just like, yeah, they did it. It's been used, and it's wrong. It's okay. It's not your fault. You found the flaw, so you're fine either way, I think.
Yeah.
Yeah, that's true.
Go ahead.
So to put Jonathan's question differently, do you expect any kind of formalize techniques to formalize which can be transferred to another setting? For example, to formalize lambda calculus, there's binder, and which causes a big problem in formalizing. There are various techniques to formalize binders, and people are thought about how binders should be formalized in Cork or Agda or something. And so your work sounds promising. I think if the underlying theory is correct, you will be able to finish it. But I'm curious to know, is this the issue of manpower problem, or are there any technical challenges in formalize all of that?
Is this the issue?
So is this to formalize these things? Do you expect a kind of unexplored area?
So if I had studied the proofs and lemmas more deeply, like what the steps are, there may be some things there that they use that are not necessarily going to fit the common world, and I'll have to cross that bridge when I get there. But I mean, if I was anticipating some issues, it would have to be doing with the idea that these were paper proofs, and this is a pen and paper method to look at complexity. And here I'm trying to mechanize it and try to apply it. So it would come from this kind of sources.
Yeah.
I think we're done.
One last question.
Last question.
Okay.
So do you think the matrix analysis that you're doing could be reused in a different context? Is it general in any sense, or like is any part of that general and used for something else? Or
Great question. We have used a very similar dependency analysis technique where we would look at how variables depend on each other, and we actually did a compiler implementation for that. It was based on if you have a variable independence, then you could split loops, and then you can pairwise them. That was the idea. So it was very much based on the kind of polynomials we get here.
Thanks.